to be here, and I'm excited to work with all of you this weekend. My talk this morning is going to be about neural interfacing, prosthetics, robotics, and how we can merge that with human physiology. And through this process, I want to show just a little bit about how we've taken a research approach, but in many ways used design thinking to get the aims of that research and identify solutions for a real clinical problem that exists all over the world. I work at the MIT Center for Bionics, and we focus in things like robotics, socket design, we do exoskeletons, neural interfacing, and most recently we've worked into optogenetics. But what I want to focus on today is this idea of prosthetics. And so there are about 7 million amputees in the United States. I looked up earlier today, and there's about 6 million here in Ecuador. And across the world, it's a big problem, mainly due to diabetes, trauma, motorcycle accidents, and things like this. And so you see over time, there's been quite a progression of prosthesis, right? So back in the very medieval days, we had just something that was made out of wood, something that was just a support structure. And today we have very fancy prostheses, things that can help you run faster, that you can jump higher with. And so one example of these is this prosthesis, for example. So this patient is wearing an actuated leg that actually allows him to go up this terrain, and with each step, there's actually energy being put in to that motion. And so it's easier for him to run up this hill. And for a traditional amputee with a prosthesis that is a passive prosthesis, walking up a hill like this with a lot of rocks is very challenging. You lose your balance, you don't have any power to go up. And so we have a lot of advancements on the prosthetic edge. And yet, about 45% of prostheses, people don't use. About 2 weeks after getting them, they try using them, and then they get very frustrated and it sits on a shelf. So why is this, right? We have so much advancement in technology going into building these beautiful, big, fancy devices, but then patients don't really want to use them. They end up using their silicone rubber or their plastic prostheses most of the time because it's just faster than having a robot, go all the way to carefully think about it, picking up something. And that's just too frustrating for us. And so when we ask this question, why, when we see so much progression in the prostheses, why is it that the amputation paradigm, what does that look like? So back in the 1860s, amputation looked very, very rudimentary. You went in, you cut off the residual leg, and you basically took all the skin and muscles and you wrapped it inside a flap, and you formed the residual limb. And today, if I look at a textbook from just 2004, it is the exact same process. So in almost 200 years, we've done nothing to improve the surgery. A lot of this is because the way that a person goes through an amputation, they first go see a surgeon, the surgeon amputates their leg, then they go see a separate physical therapist who helps them do rehabilitation, and then they go to a separate institution that gives them a prosthesis. And that prosthesis was built by an engineer who has never seen anybody else in this care continuum. And so you have these big silos between these different aspects of the healthcare system. And this is true in a number of the fields that you were mentioning the problems yesterday. One person is working on the problem, the patient is in another realm. The people building the solutions have never seen those two categories. And for all of these reasons, I think it never occurred to us that we should update the amputation surgery so that the prostheses that we build today are actually useful, that they can actually talk to the human body and receive commands from the human body. And so in many ways, my research has been integrating these silos to look at a very continuous, holistic way of thinking about the problem. And in the context of this weekend's hackathon, I want to introduce this idea of disciplinarities, right? So many of us work in an intradisciplinary environment. We have people that can do these different functions, but we don't necessarily all think the same way or overlap the ways in which we think. And so sometimes when we're stuck with a challenge, it might help to go from an intradisciplinary to an interdisciplinary approach. Or maybe that doesn't work either and we have to go to a transdisciplinary approach. And integrate just the thought processes, not just share information, but start thinking like somebody that's a doctor if you're an engineer. Or if you're an engineer, start thinking like somebody that's a business person and make sure that everything merges together. And so today my talk is going to be about cracking these interdisciplinary challenges through design thinking. So a good portion of my research today harbors on the idea of proprioception or sensory feedback. So I want us all to do a quick experiment. So close your eyes. Take your first finger and touch your nose. Okay, now open your eyes. How many of you were able to do this? Everybody did it, yeah? So how do you know where your hand is, where your arm is in space without looking at it? How can you do that? Proprioception, that's right. So what happens when you move your muscles is, say you're planting your foot down. So say you're planting your foot and you're moving your foot. Your muscles work in pairs, like your biceps and your triceps. So as you go to take a step, even though you're contracting your calf muscle, your tibialis anterior muscle stretches. And that stretch sends signals to your brain that let you know where your foot is in space, how fast it's moving, how much pressure it's applying. And using that, you can close your eyes and you can step off of a curb, you can take the next stair, no problem. Now what happens in amputation today is we cut those muscle pairs. So when one muscle stretches, the other one doesn't contract. And so you're pushing down on the gas pedal, except you have no idea how much you've pushed down. You have no idea how fast the car is moving. You have to visually integrate. And so this is really frustrating for patients. And so they have these incredibly complex prostheses. They can do all these things, but unless they look at it to see what it's doing, they have no idea. And so the question is there a way that we can actually reintegrate this mechanism, this communication modality to the nervous system? So we came up with the agonist-antagonist myoneural interface. It's called the AMI for short. And the idea is that we take those two muscle pairs that were usually connected in the human body and we reconnect them during the amputation itself. So that when one muscle contracts, the other one stretches. And so signals are sent back to the human body, to the central nervous system, about how much it's contracting, how fast it's contracting. And then we can use electrical stimuli from the external world so that when I push on the table, my biceps and triceps will know once again how much I'm pushing. And we can do this all through the prosthesis. And so we implemented this surgery in our first human patient about 3.5 years ago now. Basically, during the amputation, we had the surgeons go in and take these muscles that they usually just sever and disconnect, and we reconnected them. We harvested the biological body parts to be able to have the pulley mechanism. And so now when one muscle contracts, the other one does stretch. And these send back sensory signals to the body. And then we can use the prosthesis to actually give those sensations from the external environment to those muscles. And so we took this communication system that was broken, and we basically put it back together. And now, when we think about engineering devices, this patient is showing you what he's doing on both feet. And he can seamlessly communicate with the device without having to think about it or without having to look at it. This is one of the videos I caught actually candidly on tape. This patient was just sitting there kind of tapping her toe without realizing it. And that was really cool to see because she's not thinking about doing it, it was just kind of a natural act. Here you see the patient coming downstairs. So when we all go downstairs, we actually take our foot and we put it, plantar flex it a little bit before we hit the next stair, so we can cushion that landing. Somebody with a prosthesis doesn't think about doing this, and this is a reflexive behavior. You don't think about planting your foot. And so the test here was to see with this patient with a prosthesis naturally point his toe down. And indeed, you can actually see when he comes down that he makes that small thing to actually plant his foot. So these are kind of the initial signs that these people were starting to integrate the robot. And again, finally caught this candidly on tape. He was just sitting and having a conversation with us, and he's twiddling, his foot. And so we've done this now in about 19 patients, and it's been an incredible process communicating with the surgical team, the rehabilitation team, engineers, all of us together. A lot of our patients have gone, one is now like an international swimmer, another is a rock climber. They've gone back to their lives and are able to function with full mobility. But this only works right now in a current and a planned amputation. But what about all of the people in the world that have already had amputations? 65 are about associated with vascular pathologies, so diabetes mainly, and about 30% are traumatic. And what can we do for these people? So we found out that the human body is incredibly regenerative. You can take a nerve that has already been cut, transected, and if you place it into a muscle graft and give it some time, it will grow back. And that muscle will now act like a proxy transmitter for that nerve. And so using that, we basically tested this in preclinical animal models. And what you can see here is that when these muscles contract, indeed we can record those neural signals being sent back up to the brain from these animals. These are using just spare parts from somebody's body, so this is just muscle grafts that you take from anywhere and you place in on the nerves. And so using this, we have now a toolbox to basically take any patient that comes in with an amputation and give them the ability to signal to a prosthetic robot on the back. And so this is just one example that we've been working on, taking those neural signals from the body, communicating it to the prosthesis, and then having the prosthesis communicate back to the human. So one of our first patients lost his leg climbing this mountain in the Cayman Islands. And so we said, okay, can we build a robot to help him rock climb? And so that was this robotic foot. And he went back about 2 years after his surgery. And you can see him moving the robotic leg just using his neural signals. And he's receiving the feedback to be able to actually climb back up to his left. So throughout this whole process, I think the big learning for us was you really do have to think about the process holistically. You have to think about the process holistically. We have to look beyond what just the immediate engineering challenges. We can make these robots function faster, higher, with more force, with more energy. But it's no use unless we can integrate it with the human body more clearly. And so a big lesson here was to learn from the people that needed these prostheses. So we spent a lot of time talking to the patients, asking them exactly what do you need, what hurts, what doesn't work, what's too inconvenient. It's not enough if you create the greatest medical device or technology. If it's too hard for a clinician to do in 5 minutes in their patient room, or for some patient to put on in the morning, chances are it will likely never be implemented. And again, bringing us back to this concept of we may need to transition between a different type of thinking to be able to change the paradigm. And finally, I think a big lesson from all this research was that we have to iterate, go through it over and over and over and keep improving. And that's something that you'll definitely have to do all of today. And so with that, I'll thank you and leave us with the idea that basically we can use design thinking to solve really tough problems, to break them down into simple components. My video is freezing right now. It's not going. That's okay. We can basically take these really complex challenges and break them down into simple components. So I'll give you a little bit of an overview of today's process. We'll spend the morning, We'll spend the morning working through these toolkits, which we'll give you printed copies of. And it's very much what Yasmin showed you yesterday, where you're going to define the problem, break it down based on the stakeholders that are involved, and then build it up and make it better. And so I will hand out these packets so that you can work through your individual challenges. We'll do team pitches around 10:30. So just the groups that you were talking with yesterday night, you'll come up and just in 1 minute you'll say, we're a team, we're working on X problem, and we're thinking about doing Y, and that's it. if you need any help or expertise or a different type of person, you can say, we would like an engineer to join the team. We would need some expertise in this medical field, etc. 12 p.m. is lunch. After that, we'll do something called pulse checks. So the mentors will walk around and basically talk to each team and see how you're doing, if you need any help. 4 to 5 p.m. I know the schedule says 7 p.m. We'll do it a little bit earlier. We'll do a practice presentation. So you can come up, you just have to have bare bones slides, and you can practice talking to us. You'll get about 5 minutes today. The actual pitch tomorrow is only 3 minutes, and we'll help you work through the format and the flow and advise with the problems. And then 6 p.m. is dinner, and then you can continue to work till about 9 p.m. So that's pretty much all I've got. The only other thing I was going to mention, thank you, Yasmin, please make your slides on Google Slides, not PowerPoint or anything else. That way it's easier for us to share and integrate all the presentations tomorrow morning. Cool.